Everyone, now in this video we will see details of physical layer standardized by IEEE 802.11. In the last video we have seen protocol architecture, in which we saw that IEEE standardized only physical layer and MAC layer. So in this video we will focus on physical layer. So as we have discussed in the last video, IEEE standardizes or defines three versions of physical layer, three different transmission technologies, which out of which two of them are based on radio frequency. That means in the typically frequency band of ISM, that is 2.4 gigahertz, and one transmission technology follows infrared transmission. Although infrared transmission is now outdated and rarely used, it is still supported by 802.11 for communication inside a wireless LAN. Okay, so infrared transmission technology uses frequency whose wavelength is associated with 850 to 950 nanometer. So in case of infrared, we are talking about wavelength rather than frequency. We rarely mention the frequency. Infrared rays are mentioned in terms of its wavelength, so the wavelength should be in between this range. It uses a diffuse light for communication. That means data is used or data is communicated via diffuse light known as infrared, and which can communicate over a typically 10-meter range. Range of infrared is very short, up to 10 meter only, and that too with the line of sight connection is required for infrared. So infrared version is very old version or very basic version, which is now outdated and not mainly used by the wireless LANs because of its several drawbacks. Okay, so job of physical layer in this particular technology is the helping carrier detection, sensing or presence of carrier. That's the help that is done by physical layer to the MAC layer. Then detecting energy and doing the synchronization of receivers and different frames, all of which tasks are done by these two layers also. So details of these tasks we will discuss in these two layers. Okay, since infrared is rarely used, we will not discuss that in detail. Now the other two layers, which are radio layers, are having two types. First one is based on FHSS and second one is based on DSSS. Both these technologies we have studied in the first chapter. These are frequency hopping spread spectrum and direct sequence spread spectrum. So different networks are separated, like BSS1, a wireless LAN has several basic service set. We have seen that in the last video. And BSS2, all are connected to a distribution system via an access point. Now although they are connected to different access point, they are part of a same wireless LAN. Okay, so how they will differ from each other, that is decided by these two layers, either FHSS or BHSS. If both are using different radio physical layer, then they will be part of a different basic service set. Okay, so let's see these two radio layers one by one. So physical layer based on FHSS first we will see. Now as we know, frequency hopping spread spectrum is nothing but changing the frequency during the transmission. Okay, so now FHSS in this particular case of wireless LAN allows for coexistence of multiple networks in the same area by separating these networks using different hopping sequences. Okay, now as we have just seen, there are two basic service sets. For example, now these two will use different radio frequencies, but if they are part of a same network, then they may use same radio frequencies, but their hopping sequences will be different. Now what is hopping sequence? The way in which a data will jump from one frequency to another frequency, that pattern will change from BSS to BSS. Okay, so different BSS are separated by hopping sequences. A sequence in which data will jump from one frequency to another frequency. So how many such frequencies are standardized by IEEE? So in the original standard, 79 hopping channels are defined for North America and Europe. That means user can jump from one to another frequency in 79 different frequencies, okay, and 23 for Japan. In Japan, a user data can jump from one to another frequency in 23 different frequencies. Okay, so out of these 23 different frequencies, data can jump from any one frequency to any other frequency. Okay, so this is the standard which is followed in Europe and America as well as Japan. Okay, all other countries follow either European or American standard or Japanese standard. Okay, then the maximum transmit power, which is standardized for different regions, like in US it is 1 watt. 1 watt is sufficient for transmission in US, like 100 milliwatt with in Europe, because Europe specifies transmission power in terms of EIRP. EIRP stands for equivalent isotropic radiated power. That means isotropic means in all direction it will radiate with 100 milliwatt. So that is in Europe, and 10 milliwatt per megahertz in Japan. So different countries follow different transmission power standards. So as you can see, these are the functions related to what is the frequency hopping channels, what are the number of frequency hopping channels, what is the transmission power, it is also standardized. Then main part is modulation, demodulation and data rate. So modulation scheme which is standardized by IEEE is GFSK for FHSS. Now GFSK stands for Gaussian shaped frequency shift keying. As this is a frequency hopping spread spectrum, it is common sense that GFSK will be ideal choice. The details of GFSK is out of the scope of our syllabus, so we will not discuss what is exactly GFSK, but the modulation scheme used is a GFSK. So it has two types which is standardized by IEEE, 2-level GFSK and 4-level GFSK. A 2-level GFSK will provide a data rate of 1 Mbps, whereas 4-level GFSK will provide a data rate of 2 Mbps. Now what is 2-level GFSK and what is 4-level GFSK? 2-level GFSK means one bit is mapped to one frequency. So a user data, a single one, will jump from one frequency to another frequency. Okay, so this is F1, then F2. So 1 will jump from F1 to F2, 0 will jump from F1 to F2 and so on. So each individual bit will jump from one frequency to another frequency one by one. In 4-level GFSK, 2 bits are mapped to one frequency. So in 4-level GFSK, individual bits will not jump from one frequency to another frequency. 2 bits will combine like 10, 01, 11. Each one will jump from F1 to F3 to F2 and so on. So in a bunch of 2, frequency jumping will happen. So that is 4-level GFSK in 2 Mbps data rate. So data rate of 1 Mbps is mandatory. So anyone who wishes to implement a wireless LAN in using FHSS technology, it has to provide a data rate of at least 1 Mbps, that is megabits per second, and if you want to transmit at higher data rate, then 2 Mbps is a optional one. Okay, so this is regarding data rate, modulation, transmission power and number of hopping channels. If you observe, all these functions are of PMD sublayer of the physical layer. Okay, these are the functions of PMD sublayer of the physical layer. Physical layer has another sublayer, that is PLCP. So let's now see what are the functions of PLCP and what is the standard regarding those functions. Now PLCP functions we have seen in the last video. Now it decides a typical packet format. So FHSS physical layer packet format, that means a format in which data will be transmitted, is decided by PLCP. So PLCP defines a packet format that should be followed for communication. As you can see, a frame structure is shown over here, in which their payload is nothing but user data, which may be fragmented one also. That means user data may be divided into small fragments. Then it consists of header part and a preamble part. So a frame consists of, this is combinedly called as a frame. A frame consists of a preamble part, a header part, and then user data, that is called as a payload. Okay, now let's see bits or what are the different fields in this particular frame. Each and every frame starts with the synchronization bits. These are 80 defined for FHSS based physical layer. Okay, so 80 bits are synchronization bits, which are the first 80 bits. These are used for synchronization of potential receivers. That means access point will synchronize with the receivers, or they may be transmitters also. This synchronization happens during the first 80 bits. Okay, also during this time, that means during first transmission of first 80 bits, during that time period, signal detection or medium access detection or signal generation signal for detecting a medium will be provided by the physical layer. This signal is called as CCA. So CCA is generated and provided during the first 80 bits. So during this 80 bits, CCA signal is provided for MAC layer to sense whether medium is free or not. Okay, so these are the 80 synchronization bits. There is a fixed pattern to it. There are alternate zeros and ones, total 80 bits. So 40 zeros alternatively combined with the 40 ones. Okay, then the next field is SFD, which is of 16 bits. SFD stands for start frame delimiter. Now once synchronization with receiver is done, actual frame will start. That means it is indicated by start frame delimiter. Okay, so what does it indicate? It indicates the start of the frame and provides the frame synchronization. So if the user data is large, which is usually the case, it will be divided into small fragments. So each fragment will be associated with the preamble and header. So all the frames are synchronized with each other using this start frame delimiter. All the frames are synchronized with each other with the start frame delimiter. So remember, synchronization bits are for user synchronization, that is receiver synchronization, whereas SFD is for is afterwards, because it is used for frame synchronization. First frame should be synchronized with the first frame of the transmitter and receiver. Okay, so the pattern of this SFD is also the fixed one, 0011, 000011, and so on. Okay, so transmitter and receiver frames are synchronized with the SFD. Then next field, so this constitutes the part of the PLCP preamble. Preamble consists of synchronization and SFD, that is 96 bits. Then starts the header part, which is of 32 bits. Okay, in this header part, first 12 bits are PLW bits. 12 bits are PLW bits. PLW stands for PLCP PDU length word. PDU is a packet data unit. That means it indicates length of a payload, including 32-bit CRC of a payload. So how much payload, that is user data, is contained within this frame is indicated by PLW. So how much data we can attach in a single frame? Maximum of 4096 is a size of a payload, out of which 32-bit will be CRC. So user data will be 4096 minus 32. That answer comes as 4064. So 4064 are user data and 32 bits are CRC bits, that is used for error detection and checksum. So that is indicated by PLW. So this is the maximum value. You can use any number of bits for payload up to 4096. You can use 1000 also. Out of 1000, 32 will be for CRC and remaining 968 will be for. So if there are 1000 bits in the payload, that means 968 bits of user data and 32 bits of CRC. Okay, so that is the meaning of PLW. Then next field is PSF. Let's see what is PSF. PSF indicates PLCP signaling field. It is of only 4 bits, so it has a fixed defined meaning. Now it indicates the data rate of the payload. We have seen different data rates are supported. 1 Mbps is mandatory, 2 Mbps is optional. Now modern day wireless LAN are also capable of higher data rates, so that is also can be indicated in this PSF. So all zeros, that is 4 bits, all 4 bits are 0, that indicates 1 Mbps. If the 4 bits are 0010, then it indicates 2 Mbps. If all bits are 1, that indicates maximum data rate of 8.5 Mbps. This is not in the original standard, but nowadays 8.5 Mbps is also supported. Okay. Apart from it, if any other combination is used, then that is a invalid data rate indicated. Okay. So PSF has only 3 types of combination: 0000, 0010 and 1111, indicating different data rates. Then finally there is a 16-bit HEC, that is header error check, which provides a protection to the header. So this HEC field will protect only the header. Preamble is not protected, or payload is also not protected. So in transmission, if payload is corrupted, you cannot change or you cannot identify it. But if header is corrected, it can be identified via HEC. So simple CRC mechanism is used for protection of header. CRC with generator polynomial, which is given here, is used for providing the CRC checksum. Okay. So the final part is nothing but payload. We have discussed maximum size of this payload is 4096, which will contain 32 bits of CRC also. Okay. So this is a physical layer packet format for FHSS. Now the third radio transmission technology, that is DSSS. First was IR, second was FHSS. Third radio transmission technology is DSSS based. Now in this, different networks, that is different BSS, are separated by code rather than frequency. So both BSS can use same frequency, but their code will be different. Okay. So network separation by code and not by frequency. So if you recall, DSSS requires a chipping sequence that will be XORed with user data. User data is XORed with chipping sequence to obtain a DSSS signal. So chipping sequence used is nothing but a Barker code, which we have seen again in the first chapter itself. So chipping sequence used is a Barker code. In FHSS, hopping sequence was there. In DSSS, chipping sequence is there. So that is a chipping sequence. Then modulation schemes are either DBPSK or DQPSK, depending on type of data rate that you want. So DBPSK modulation is for 1 Mbps and DQPSK modulation is for 2 Mbps data rate. So DBPSK stands for differential binary phase shift keying and DQPSK stands for differential quadrature phase shift keying. Now again, details of what these modulation technologies are, that is out of our scope of our syllabus, so we will not discuss that in detail. So remember, these modulation schemes are different. Since this is code related, we are going for phase shift keying. If it is frequency related, that is FHSS, we will go for frequency shift keying. Okay. Now another important aspect is preamble and header, which is part of your frame, is always transmitted with 1 Mbps and payload may be transmitted with 1 or 2 Mbps. So you cannot change the data rate of preamble and header. You can change the data rate of payload to 2 Mbps. That is data rate. Then finally, radiated power similar to FHSS, 1 watt in USA, 100 milliwatt in Europe, and minimum of 1 watt in 1 milliwatt in other countries, that is Japan and other rest of the countries. Okay, that is standardized by the IEEE. Again, if you observe, these are all specifications of PMD in case of DSSS. That is PMD sublayer of the DSSS based physical layer. Now PLCP sublayer of DSSS based physical layer again will contain, or it will define, a packet format. So packet format decided by PLCP sublayer for DSSS based physical layer is given on your screen. Again, if you observe, it contains preamble, header and payload. Now preamble fields are same to that of FHSS packet format, but size is different. Now synchronization bits are changed from 80 bits to 128 bits. Okay, as in the FHSS, these synchronization bits are used for receiver synchronization, adjusting the gains of antennas of transmitter and receiver, producing carrier sense signals, that is CCA, and providing frequency tuning, that is frequency offset compensation. Okay, so same function, only the time allowed is a larger one, from 80 bits to 128 bits. Okay, then 16 bits of a SFD, same as that of packet format for FHSS. Start frame delimiter used for frame synchronization. First frame of receiver should match with the, or synchronize with the first frame of the transmitter at the beginning of the frame, and the pattern is also fixed one. These are the 16 bits which are used for frame synchronization. This is different from FHSS based SFD because the sequence is different. Then preamble part is same, size is larger, but header part is now modified to 4 fields rather than 3 fields. Now PSF field is replaced by separate fields like signal and service. Now signal field indicates data rate of the payload, similar to the PSF field. 1 Mbps, which is used for dBPSK, indicated by 0A. 0A means this is a hexadecimal, that means 4 zeros, and A means 1010. So if signal field contains this combination, it means the 1 Mbps data rate and dBPSK modulation. If it contains 14, that is 0001, that is, and 4 means 0100, so it indicates 2 Mbps data rate and DQPSK modulation scheme. Okay, this is signal field. In FHSS based physical layer, it was PSF field. Now it is signal field, which is of only 8 bits. It is not mentioned here, but it is of 8 bits. Okay, 8 bits. Now signal field is followed by service field. Again, it is of 8 bits. Service field is reserved for future use, but it is filled with all zeros, that means 8 zeros, to indicate that this frame is a 802.11 compliant frame. This frame is for wireless LAN, that is indicated by all zeros. Okay, after that, similar to PLW, length field is there. Length field is of again 16 bits. It indicates length of a payload in microseconds. Remember, this length is mentioned in terms of microsecond. Now how can we mention the length in microseconds? That means, let's say 16 means maximum length can be 2 raised to 16. So let's say length mentioned is 1000. That means 1000 microseconds will be required to transmit this payload, that is indicated in the length field. 1000 microseconds will be required to transmit the payload, that is indicated in the length field. Okay, then followed by final part of the header, that is similar to the previous physical packet format, that is FHSS. It is called as HEC. Again 16 bits. It protects the header, that is signal, service and length, and it is using a CRC with generator polynomial of same as that of the FHSS. Again, payload is not protected, only header part is protected, and followed by the payload. Okay, so this is regarding physical layer of the wireless LAN infrastructure based networks. 3 versions are there, that is 3 transmission technology. One is based on infrared and 2 are based on radio frequency. Out of the radio frequency, one is based on FHSS and another is based on DSSS. PMD handles different standard for modulation, demodulation, transmission power, etc., whereas PLCP handles the packet format. Okay, so in the next session we will see details of MAC layer in case of wireless LAN. That's all for today. Thank you.